Today we're going to talk about Newton's law of universal gravitation. After Isaac Newton had developed his three laws of motion, there was still something that bothered him, and that was the planets. He couldn't quite figure out what force kept the planets in what he thought was a circular orbit around the sun. And likewise, what force kept the moon in what he thought was a circular orbit around the Earth. At the time, no one had a conception of gravity. And there's an old fable about how one day Isaac Newton was sitting under an apple tree, an apple fell out of the tree and fell to the ground, and he had his eureka moment that the same force that pulls the apple to the ground is what keeps the moon in orbit around the Earth. Whether it actually happened that way or not isn't important, but what he came up with is if you have any two objects that have a mass, so this label this one M1 and M2. This object has a mass of M1. This object has a mass of M2, and they're a distance d apart. They're going to exert a force on each other, and that force is proportional to the product of M1 times M2 divided by d squared. Now, Newton couldn't calculate the actual size of the gravitational force, but he did come up with this idea that the gravitational force is proportional to the product of the masses and divided by the square of their distances. Now, it's important to note here that this gravitational force would be calculated exactly the same way for M1 as it is for M2. They exert the same size force on each other. Now, about 150 years later, a guy named Henry Cavendish actually did an experiment where he measured what's called the universal gravitation constant. I'm not going to try to explain how he did it, but he did it. And he measured the universal gravitation constant to be 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. So this is a very extremely small number, which tells you that gravity is a very weak force. Now, here on Earth, if I were to jump out of a window, I wouldn't think it was a very weak force, but it is a weak force. It's only very strong here at the surface of the Earth because the Earth is so massive. If I put the mass of the Earth in this equation, M1 would be very big, which would give me a big gravitational force. So anyways, after Henry Cavendish did his experiment, we could put that G, capital G, into the equation for gravitational force, and we have the gravitational force equals 6.67 times 10 to the negative 11 times M1 times M2 divided by d squared. Now, we can use this to calculate any gravitational force between the Earth and the Sun, the Earth and the Moon, etc., etc. You can also use it to calculate the gravitational force between you and the Earth, your weight. And to do that, you would use the radius of the Earth. So one thing I kind of skipped over here is that this distance d is from the center of one object to the center of the other object. I know I didn't draw it that way, but that's how it's measured. So if you want to find the gravitational force acting on you at the surface of the Earth, you have to use the distance from you to the center of the Earth, which is the Earth's radius. So if you were to do this, you would get your weight in newtons, and it should come out almost exactly the same as your mass times 9.8 newtons per kilogram. Now, to calculate an object's acceleration on a planet, you know that the mass of the object does not affect the rate at which it accelerates, so we can take the mass of the object out of this equation. And by the way, MO is mass of object, MP is mass of planet. So if I take the mass of the object out of this equation, I have an equation for acceleration, or gravitational acceleration, which we use the symbol lowercase g. It would be big G times the mass of the planet over the radius squared. Now this is assuming you're at the surface of the planet. If you're away from the surface, you would just add on to that r.